Yeah, diatomic.
Yeah, or you know, molecules or compounds. I use molecules and compounds interchangeably. I call them all molecules. If you've had chemistry, there's some difference between them that I can never keep in my head what the difference is.
I can understand what you're coming from, though.
Okay. Difference between a molecule and a compound? Okay. Also, if I ever talk about air molecules, I understand that there's no such thing as an air molecule. They are molecules in air. The molecules are made of other things. Air is a combination of all those molecules. So air molecule is just a generic term for the molecules of the gases. All right, so I take my electric field and I move it over to here, and I change in my electric flux, which creates a magnetic field. Now suppose I then come back. So I move my charge over to here and then back. Which means that my electric field changed when I came over here, but then it changed again. So I have a change in the change in electric field, which causes a change in my electric flux, which causes a change in my magnetic field. We're good so far. It is leading somewhere. Hold on.
Is it too much of a jump to say that Maxwell is the first to discover that electricity and magnetism are interlinked?
Oh, no. That'd probably be Faraday would get credit for that.
Oh, okay.
And the story, and I've heard it attributed to various physicists, but the story supposedly is Faraday, after he figured out there was a connection there, had a press junket briefing, telling the press, and they asked, of what use is this? To which Faraday supposedly replied, of what use is a newborn child? The basis of power generation throughout the world is based upon this idea, well, basically what Faraday found conceptually.
I remember one quote he said where a politician asked him, why is electricity important? And he said, one day you may tax it.
Ah. And they do. All right. So if I have a change in my magnetic field, that means I have a change in my magnetic flux. So a change in the magnetic field causes a change in my magnetic flux. If I have a change in my magnetic flux, I'm going to create an electric field. So this causes a change in my electric field. Now, that was I took the electron here and I took it back. Well, I suppose I just take it back and forth. So I've got however many changes of this, which is how many changes of that, changes. So basically an electric field creates a magnetic field, which creates an electric field, if I'm oscillating this back and forth. Maxwell went on to theoretically come up with the speed of this electromagnetic wave. And he mathematically came up with, it is 1 over the square root of mu sub naught epsilon sub naught. And I didn't actually say what mu sub naught is, that's this right here. This is known as the permeability of free space. And its value is 4 pi times 10 to the negative 7th. I believe it's Tesla meters per ampere. Just verify that. Nope. It is not on the front or back cover. They've let me down. Okay.
Is there a formula for the permittivity of free space?
You all, it's basically this right here.
Oh.
Because mu sub naught is exactly 4 pi times 10 to the negative 7th. I'm pretty sure those units are right. speed of light at this point has been set. The powers that be have come up with it, but let's actually make that final connection. So Maxwell derives the speed of the electromagnetic wave, because basically we have an electric field creating a magnetic field, creating an electric field, which creates a magnetic field, and so on. This thing goes on forever until it's absorbed. And so if you did 1 over the square root of, at this point, these were found experimentally, 4 pi times 10 to the negative 7th times 8.85 times 10 to the negative 12th, and then square root of all that. And Aaron is going to share what he finds.
What's the other one? 8.85 written here, 8.85. 12.
There we go. All right.
Very big number. There's like, see if it breaks down the engineering notation for me. It's like 2.998 times 10 to the 8th.
And since this is a speed, what are the units?
Is it speed? So meters per second.
Yeah.
So it's really long.
Yeah. About 300 million meters per second. Which means in a nanosecond it goes, this far? Ish. All right, so. No, a third of a meter. It goes about that far in a nanosecond. All right. So Maxwell comes up with this, and then in a moment of humility, recognizes that this is close to the experimental value for the speed of light, and says, I think light is an electromagnetic wave. As opposed to the less humble saying light is an electromagnetic wave. He says, I suspect that it is an electromagnetic wave. And so that is the nature of light. So Maxwell, even though this is the part he did, he does derive a value which turns out to be true, that light is an electromagnetic wave. And so somewhere along the lines, the whole collection of equations does get Maxwell's name. So, because light is an electromagnetic wave, because all you need is the electric and magnetic field sort of propagating themselves, you don't need a medium. Light does not have to travel through some sort of material, which is fortunate because there's not a lot of material between the sun and the earth, and light can get to us. However, that didn't stop people from speculating, because they knew light was a wave. There was evidence for it, and we'll get into that in a moment. And if waves, so prior to Maxwell, if waves require a medium, there must be some medium in outer space. So they came up with a name for it, or they used a name for it.
Dark matter or dark energy.
Say again?
The dark matter
Oh.
or dark energy.
Yeah, that was this is way before they ever thought of that stuff.
Yeah, that are theory.
So what they figured out was that there's something called ether. Ether. I have some textbooks which refer to light as ether waves. So an electromagnetic wave and in parentheses I'm going to write down ether wave So if you see a reference to it, probably not many textbooks will use this anymore. The experiment that is now credited with saying that ether does not exist in outer space. The first experiment was 1890s, and I have a textbook from 1940 which still refers to ether waves. So it takes a while from the definitive experiment to things actually making it into textbooks. And it was probably called ether waves because the guy who wrote it was old, and that's what his teachers had called it, because that's what his teachers had called it. And you know, at some point, some student's going to go, wait a second, that's not the current research is not calling it that anymore. So when I make a reference to light, I'm making reference to an EM wave. I should specify that if I'm talking about that which we see, that is visible light. Now, I'm not going to say I'm doing this 100% just because there's habits that have been developed over the past several decades, but visible light is specifically that which is within the normal human perception. In everyday life, they generally talk when there's a reference to light, it is a reference to that which we see, but in physics, we really should differentiate. Light is a much broader term. Microwaves is light.
Infrared.
Exactly, that too. Ultraviolet.
Gamma, X-ray.
Yep.
Radio waves.
Radio wave.
Yeah, radio.
Radar.
Well, radar is radio.
Oh, yeah.
And then you get into the VHF, UHF. I don't know if any of you have ever seen a TV with those on it.
I've seen the term before. I've seen those before.
Did you know radar is actually an acronym?
The radio.
Radio detection and ranging. Same as sonar, sound navigation and ranging.
So the sonar would be using the stuff from the first 4 chapters we covered so far. Now we're getting into stuff that would cover radar. All right, so some of the properties of light. Make sure I don't get anything. So it travels in and I'm going to put straight in parentheses and quotation marks here, in a straight line. I think your textbook says straight line. Yeah, light travels in a straight lines, and I want to talk about when that does not happen.
Like a prism.
All right. So we can sort of add on to this with slightly more accuracy within a constant medium. So when you get to the prism example, that it's entering a new medium and therefore it takes a new straight line. However, I still want to keep straight in parentheses and quotation marks there, because
It can be affected by gravity, right?
pardon?
It can be affected by gravity, right?
Yep, and that's where I'm heading. It might seem to the light, let's give the light sentience here. The light is traveling in a straight line, but but from a different point of view, it's not straight. For example, I am going to assume that that ruler is straight. And so would you agree that this line is straight?
Yeah.
Is the line straight now?
Yes. Sorta.
Yeah, I think the sort of pretty much covers it. From the point of view of the paper, it's still straight, but the point of view of looking outside of it, it's not. And the same is true with light and, as Alex said, gravitation. That if I've got the sun here, what's that? And Earth, not the scale. that if I have a distant star over here, then the light from that star is traveling straightish line. It's going to get curved by the sun and then hit us here. But if this is directly behind our sun, then light should travel from this side and hit us here. Now, it's not easy to see. If you went outside and stared at the sun, one, don't do it, it's a stupid thing to do. But if you had the proper protection, you would potentially see something coming from more than one direction. If in a two-dimensional universe here, it would look like the object is here, it would look like the object is there. Technically, if it's perfectly lined up, it would look like a ring, because it's coming from all directions. And this was first seen in 1919, I believe.
So someone was staring at the sun. Someone was staring at the sun in 1919.
Well, there is one time when you could look at the sun.
Oh, yeah,
A couple of years ago,
yeah.
went down to South Carolina to do it.
Oh, yeah, I did that. That was incredible.
The eclipse.
Yeah, if you ever get a chance to see a total eclipse, it is worth it. It was about a minute and a half. It was worth the 2 or 3 hour drive to get there.
You have to wear those like little sunglasses things.
As soon as the sun's completely blocked out, you can take it off. But until then, yes, please make sure you're wearing the proper protective eye gear.
It was pretty awe-inspiring watching things darken for a bit, that brief
Yeah.
time. I could easily see why people who didn't understand astronomy would have been so freaked out.
Yeah. Fortunately, we know better now. But it is absolutely amazing. But the moon just happens to be the right distance between the Earth and Sun. It happens to be just the right size. It is perfectly lined up to be able to block. Again, not to scale. And so you block this out and you actually can see that. And then also we have enough telescopes in outer space. I think Hubble picked it up, and there are pictures out there of something perfectly lined up and you actually see the smear of light going around. This is known as gravitational lensing. First predicted by Einstein, first discovered by Eddington.
There are another same effect like this on I think it is 2018. 2018, yeah. They say 4 supernova at the same time. But it was actually one supernova, but they see 4 images of the supernova. Did you hear that?
I got supernova.
Yeah, they see on the Hubble telescope they see 4 supernova at the same time. So, but it actually only have 1 supernova, but because of the gravitational lensing, they see 4 supernova at the same time.
Ah, okay.
Yeah,
Oh, all right.
and it bigger years bigger than last year's way.
Okay. It still amazes me, anything with astronomy, how we are on one planet and one spiral arm of a galaxy, and there are billions and billions of galaxies, and we know anything. The amount of stuff that we can see is just, and make theories about, just mind-boggling. All right, so, number 2, another property of light. Reflection. Light seems to bounce off things. Not an earth-shattering concept for anyone who's looked in a mirror. And then the angle of incidence equals angle of reflection. So this is incidence, and reflection. So if I have a flat mirror here, if I have light coming in, it should bounce off. Typically, when you're talking about angles of reflecting, it is from from the perpendicular or the normal to the mirror. So this would be, if light's coming in that way, this is the angle of incidence, this is the angle of reflection. And there are many things that do that, so. Even saw it in an episode of MathNet. MathNet, anyone? Anyone have memories of this? Square One Television?
I don't think so.
Yeah. All right. There's also refraction. This is when it enters a new medium, it will change course. So if I have, let's just say this is water and air, if light is coming in, then it bends. So this would be the angle of incidence and the angle of refraction. And they are not equal. We'll get into more detail on that one later. And the fourth one, diffraction. And this is light interfering with itself. Now, most of you can see a little bit of diffraction going on. If you hold your fingers together, if you've got a small little gap between your fingers and hold it up to the light, you see little black bands. That is diffraction. Not everyone has those gaps between their fingers, but if you do. When I was a kid, and I noticed that when I was a kid and thought it was just tiny little hairs, but no, it's not. It's the light interfering with itself. This is known as single slit diffraction. And although, yeah, we'll get into that later. Basically in this order, we'll do reflection, then we'll talk about refraction. And so reflection, mirrors, curved. Refraction, we'll get into lenses, and then we'll start talking about diffraction. So that's pretty much the order we're working. All right, so here's one of the big questions that were one of those hot debate topics from the times of Newton. We haven't figured out now, but is light a wave or a particle? Maxwell's 1870s, Newton, late 1600s. There are two competing theories. Newton versus Huygens. Newton was a particle guy. Huygens was a wave guy. Light traveling in a straight line, well, that makes sense if it's a particle. I shoot a particle in that direction, it goes in that direction. So this is best explained by particles, although you can make it a wave argument for it. Reflection, the fact that it hits and then bounces off at the angle at which it hit. Well, particles explain that one pretty well too. Waves, you can make an argument, but particles really works better for that one. Refraction, well, you actually could go either way on that one. Waves actually work a little bit better for refraction, but you can make a particle argument. There's a calculus problem I remember doing when I was in high school. That this is the beach, and this is water. You're a lifeguard, and there's someone over here who needs saving. So someone who needs saving. Or perhaps it's swans. And you want to get from here to here as fast as possible. Well, if you go in a straight line, you can run on the beach faster than you can run in the water, than you can swim in the water, so you're spending more time in the water here. If you went this way, till you were straight up next to them like that, then you're spending more time on the beach than necessarily you need to. And there actually is optimum to get from here to here the fastest. Based on how fast you're running on each. And if you work through the math on it, it directly matches this idea of refraction and how fast light travels in the different mediums. And then there's diffraction. If light is a particle, particles cannot explain this. So this is the big thing, especially, so the debate rages back and forth. Newton, discoverer of calculus, and able to derive Kepler's principles or Kepler's laws based on some simple principles. So he was just the heavyweight at the time. If he had said that light came in the form of ducks, there's probably a large segment who would have believed it, because it was Newton. Huygens, though, had a lot of other stuff on his side. And then in early 1800s, there was the double slit experiment. So the double slit experiment, more sophisticated than, looking at the cracks between your fingers. Light is sent in, and there's two slits here. And if so light's gonna go through the two slits. You can think of this as like water rippling through. And then you have these two sets of lines coming through as it ripples out. And so wherever they overlap, that's when you have two peaks. This is when you have constructive interference. And then so this is, so I have constructive interference here, and then halfway between I have destructive interference. And so what I would expect is at various points that the light would be bright and other points it would be dark. So very, very much like the sound waves when we were dealing with beats. So if you show this up against, if you had some screen there, what you would expect is the light to be brightest in the middle, then a little less bright as you go out, but you would expect to see a pattern like this if light was waves, and we in fact do see that. We will replicate this in lab. If it were particles, and a horrible marker, and a less horrible, but still horrible. If light were particles, then what you would expect is, as the light goes through the double slits, you would expect a whole bunch of light here and a whole bunch of light here. But that's what we see. And therefore, it's obviously a wave. About 7 decades later, Maxwell comes up with this electromagnetic wave that happens to have a speed very close to the experimental speed of light. And so that pretty much clinched it for a couple of decades. Yes?
It's that experiment they call it a superposition, right?
Say it again?
It's that experiment they call it superposition.
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 Yes.
Yes. Very much.
And it means two waves at the same time.
Right. Well, you send one wave and it happens to go through each slit, creating, I guess, two smaller waves. So that, yeah, so it would be two waves here interfering with themselves. But it's all started from the single wave. And then, someone said, suppose we did this with electrons.
Is this the one where like it was different when they observed it?
Yeah.
Yeah.
So, because electrons, clearly electrons are particles, there's those things that go around the nucleus. Or are they? We have a screen over here. Now you send an electron this way. You shoot it at the target, and what you would expect, since electrons are particles, is you would expect a whole bunch of electrons to be hitting somewhere around here and some hitting around there. You have some sort of surface here that scintillates. In other words, when the charge hits it, there's a bright dot. Or you could have some sort of Geiger counter which picks up I guess it'd be beta radiation. So when you send a bunch of electrons at it, you also get a whole bunch. It doesn't look like, it's not really a wave pattern in the same sense as light is, but what you have is you have an electron hit here, and then hit here, and then here, here, here. A bunch hit here, not as many hit here, you got a bunch hitting there. And if you look at a sort of histogram of it, most of the electrons are hitting in here. Then you got a period where no electrons hit, and then. So you get a very similar pattern. And then they sent one electron at a time, as opposed to a whole bunch of electrons, because suppose you send a bunch of electrons, well, possibly, it's hitting here and it's rebounding, or, you got these collisions not in air, but you have these collisions which is causing this. So you send one at a time and you get the same type of pattern. And then they said, well, what slit is it going through? So they put a detector here. As soon as they put a detector there, they were getting this pattern. So, the electrons seem to have wave kind of properties and particle properties.
So that was the genesis of the wave-particle duality.
Yeah, actually it was speculated first with light, and then they extended it to things that were classically particles.
Oh. And that's also where Heisenberg's uncertainty principle comes from? Well,
That one's, it is related, but we'll get into Heisenberg near the end.
okay.
All right, so we have these various properties here. It's not as simple as was once thought. Newton did actually use the term wavicle. It didn't really catch on because at some point they said, well, clearly it's not particles.